Well, very good morning to everyone. On behalf of the Department of Aeronautical Engineering, I hereby welcome Dr. S. Gurusideswar, Assistant Professor of Aerospace Engineering, SRM Institute of Technology, Chennai. We welcome you, sir.
Thank you.
Thank you for being here and thank you for accepting our invitation. May now I request Ms. Dixia Sambial to give the brief introduction about our resource person. Over to Diksha.
Albert Einstein once said, "Intellectual growth should commence at birth and cease only at death." A very good morning to one and all present here. It's my immense pleasure today to introduce you all to such an eminent and intellectual personality present among us all, Dr. Gurusideswar S. Dr. Gurusideswar S is currently working as an assistant professor in the Department of Aerospace Engineering at SRM Institute of Science and Technology. Prior to this, he has worked as a postdoctoral fellow in the Department of Mechanical Engineering at IIT Bombay. During his postdoc tenure, he has worked on dynamic characterization of ultra-high performance concrete UHPC materials, which is developed for blast and impact resistant structures. He obtained his PhD degree from the Department of Aerospace Engineering, IIT Madras. During his PhD tenure, he has developed expertise in various experimental techniques for characterizing material properties of nanocomposites. He has over 5 years of teaching and research experience, and he has authored several research papers in reputed journals and monographs. He has also published a patent on high strain rate tensile setup by impact loading in Indian Patent Office IPO. His research areas include mechanics of materials, polymer fiber reinforced composite, ultra-high performance concrete, smart material for ballistic applications, non-contact strain measurement technique, fracture mechanics, and a lot more. Thank you so much for joining us today, sir, and I'm sure we'll all get to learn many things from you. Thank you.
Thank you, Ms. Diksha, for your brief introduction. Very good morning to all the participants. I'm very happy to be here. I thank the organizer for inviting me to give a presentation on this FDP on advancements in aerospace materials, manufacturing, testing, characterization. Thanks again to the organizers. So let me present the screen. I hope my screen is visible to all.
Yes, sir, it's visible.
Okay. Thank you. Fine. So this is my topic. Today I'm going to speak on this topic, high standard characterization of composites. So let me give the roadmap, what I'm going to speak in this 1 hour. So I'll be briefing about the nanocomposites, some introduction about nanocomposites. Why do we go for nanocomposites? And I will be talking about how to prepare nanocomposite samples. And the main important thing, the part is the microstructural characterization. So how are we going to understand the dispersion of nanoparticles in the matrix? So for that, we are going to see different microstructural characterization, and then we are going to see about the mechanical characterization of nanocomposites. And then I'll be coming to the main objective of today's talk, that is high standard testing. So why do we go for high standard testing? So this I'm going to explain in today's talk. And also I'm going to talk about this digital image correlation technique. It's a very advanced technique. It is also called as non-contact strain measurement technique. So I'm going to discuss about this technique in today's talk, and then I will be sharing my results from my research work on high standard characterization and concrete remarks. So, and also I will be giving some idea about the future scope of this work. So this is the roadmap of today's topic. I will be explaining each topic one by one. So we all know what is nano. So it's 10 power minus 9 per meter. So we can define nanoparticles which has the particles which have a dimension of 100 nanometer or less than 100 nanometer. This should be differ measurably than those of bulk material. So this called nanoparticles. And then what is the nanocomposites? So when we combine this nanoparticles in a matrix, then it is called nanocomposites. So we know composite materials that combine one or more separate components in order to improve performance property. So if I disperse a nanoparticle in a matrix, then I can call it as nanocomposites. So the purpose of going for nanocomposites is to have better performance. So that's why we disperse nanoparticles in a matrix. This is called nanocomposites. Then here I'm going to talk about different nanofillers. So this nanofillers researchers have been using for a long time, since 2 decades. So I will be giving some idea about different types of nanofillers which we use for different applications. So we can categorize the nanofillers based on its shape and size. You can see the nanoparticles come in layers. You can see it's like a layer where we have the thickness is nanometer. That's why we call it a nanoparticle nanofiller, wherein the other dimensions are in micron size. But still, its one dimension is in nano. So that's why we call it a nanofiller or nano layer. And if you see example, I can say clay. A clay is an example of nano layer. And then we can see about nanotubes. We can see the you can see the diameter of the nanotube is less than 100 nanometer. So we can say it's an example of particle nanofiller. So the very common example is carbon nanotubes. And we have many nanoparticles which has different shape, which has sphere shape, which has hexagon, like that. We have different types of nanoparticles. So just I have explained the different types of nano particles based on its structure. So it's ranging from layer to tube to different 3D shapes. So nanocomposites. Let us discuss about nanocomposites, because in this whole talk I'll be focusing on nanocomposites. So it's a two-phase material. As I told earlier, say composite, then we can say it's a two-phase material. Again, you all know what is composites. It's a two-phase material. The main the important significance of composites is we can tailor the properties. So based on our requirement, the properties can be tailored. So that's why we go for composites. Again, it has 2 phases. One is reinforcing phase and the matrix phase. So we can categorize the composites based on its reinforcing phase or matrix phase. So if I take reinforcing phase, then we can have fiber composites. Then we have particle composites. Then we have flake composites. If I categorize the composite based on matrix, then we have polymer matrix composites, we have metal matrix composites, and we have ceramic matrix composites. So like that, the composites can be categorized based on the fiber and the matrix. Based on the type of reinforcement and the matrix, we can categorize the composites. So now we are going to see nanocomposites in today's talk. So it's a two-phase material. So where one of the phases is dispersed in the second one on a nanometer level. So that is called nanocomposites. So in this work, we have chosen the clay as a nanoparticle and the matrix as a epoxy matrix. So, so we are going to disperse the clay in the polymer matrix. So that's why we say it's a polymer nanocomposite. So again, I have here we can see the different about the definition of clay. So it's a layered silicate. So it is naturally available. It's consists of very thin layers that are usually bound together with counter ions. And as I told earlier in my previous slide, I have given example of nano layer. You can see it is here. It has a layer thickness of 1 nanometer, and the lateral dimension may vary from 30 nanometers to several microns. So, so because of this reason, we have very good aspect ratio. So the length by thickness is aspect ratio. So with by using nano clay, we can get a very high surface area. So it's come around 1,000, greater than 1,000. So this here I just given this the chemical definition. The layers are separated by its regular van der Waals gap. That is called interlayer or gallery. So that we'll discuss in our future slides. So clay structure. So here I have given that the structure of a nano clay, and the right hand side shows the typical scanning electron micrograph of a raw clay. So this has been taken at around 23,000 x magnification. So you can see it's like a layer. It has a nano size thickness and it has a micron size length. But this clay is in raw form. It is in agglomerated state. But this clay is not dispersed in matrix. So simply we have taken a pinch of clay and we got this micrograph. So this was taken from scanning electron microscopy. We say SEM. So you can see this is the micrograph of nano clay. So before going to further discussion, let us focus on different types of clay. So as I told earlier, it's a natural sucking after turtle. So based on this formation of layer silicates, we can categorize into different types, phyllosilicate and pectinite. Like that we can categorize. These are the different types of clay available. But among this, we have found this Mont Morillonite clay is very attractive. So we have chosen this MMT clay for our research work. So again, here I have given some significance of MMT, that is Mont Morillonite clay. It has high aspect ratio. It has unique intercalation acceleration characteristics. This I will come back to this terminology later. And it has high specific surface area, and it is environmentally friendly, and it is readily available in large quantities with low cost. So because of these reasons, we have taken this Mont Morillonite clay for our research work. So again, this slide gives some idea about different types of commercially available clay. As I told here, this nanocomposites, this field has gone up in recent decades. So several researchers have worked on the area, and also this clay is many different types of clay are available commercially. So here I have given some commercial names, like from Southern Clay Products, we have this Closite, we have Garamite, and this is the clay which we have used for our research work. And we have clay from Bentone from Elementis, and we have from and we have clay from Germany product Danofil. Like that, there are many different types of clay which are available commercially, and also we have different types of clay. One is pristine clay, that is unmodified clay. Also, I will come back to this point later. Why do we go for modified clay? Yeah. So this is the types of clay which many researchers are focusing on this types of clay. Yeah. Let me come to the important point of this clay dispersion. So this is the layered silicate. Already I have discussed about layered silicate. So to prepare the nanocomposite, we need to disperse or mix the clay with the polymer. So when I mix the clay with the polymer, I will end up with 3 different types of dispersion. So you can see, one is phase separated microcomposites. If you see in this phase separated composites, you can see the particles are in agglomerated stage. You can see this is the one type of structure we get, and then intercalated structure. So this is a structure which we can get a very good dispersion. You can see it's intercalated, where the clay has been arranged, dispersed in a parallel fashion. You can see the figure. You can see the laser. The third one is exfoliated. So this is the structure which we want. So here you can see the clay has been dispersed randomly, and we have good dispersion. So this good dispersion of clay in a matrix will lead to improvement in the properties. So we focus on this dispersion, but it is difficult to it is not easy to get this dispersion. We need to follow some techniques to get this good dispersion. Let us see in detail in our next slides. So in this slide I wanted to convey that by mixing a nano filler in a polymer, we end up with 3 different types of structure. So one is phase separated, and is intercalated, and exfoliated. So among these 3 structure, we focus on exfoliated. So this is the structure which we want, and from this structure we can get a very good improvement in the mechanical properties. Okay, this here I have just given the history of nano clay. So it has been used by Toyota researchers in Japan in 1990s. So they discovered this possibility to build a polymer layered silicon nanocomposite. So they dispersed this nano clay in a polyamide matrix, and then they fabricated the nanocomposite, and then they did a lot of characterization, and then they found the addition of nano clay in polymer matrix lead to very good improvement. So this is the very first the research made on nano clay, and then later it was extended to epoxy. So earlier they focused on polyamide, and then many researchers they extended this work to different polymers, not to epoxy, polyester, like that. And then they have conducted many work on this area. Yeah, so now so far I have talked about what is composite, what is nanofiller, what is nanocomposites, and different types of nanofillers, and about the dispersion of nanofiller in epoxy, and then history of nanoclay, like that we have discussed so far. Now let us see how to prepare the nanocomposite. So this is a very important topic, right? So let us see how to prepare a nanocomposite. So in this work, we have used epoxy. Epoxy is a thermoset polymer. We have used digyl-cidyl ether bisphenol A resin. It's a commercially available resin, which was bought from Huntsman supplier. And then we used tetra curing agent. So we have 2 different types of curing agent. I hope many of you in this area. One is anhydride and amine type curing agent. This type of curing agent we can keep in room temperature itself. And then we also focus on hybrid nanocomposite, because we wanted to understand the effect of clay on a traditional composite. So in the whole work, we are going to see 2 different types of material. One is purely polymer epoxy clay nanocomposites, where we disperse the clay in epoxy. And the second one, we are going to disperse the clay in a traditional composite, like a traditional FRP composite. So we have used a e-glass fiber, which is commercially available. It's a oven type fiber. It has 16 GSM, grams per square meter. So this is the primary reinforcement, and we add clay as a secondary reinforcement. So as I told earlier, we used modified Mont Molinite clay, and the commercial name is Garamite 1958, which was supplied by Southern Clay Products USA. So here, so now to prepare the nanocomposite, we need to do the design of parameters. So we need to focus on how much amount of clay I'm going to add. So based on this survey, we have found that higher clay weight percentage lead to poor dispersion. So this is what we understood from our test survey. So that is why we stick with 5 weight percentage. So if we go beyond 5 weight percentage, then we may not get good dispersion of nano clay with polymer. So that's why based on the survey, we have chosen these 3 parameters. So example 1.5 weight percentage means we take 100 gram of resin and we take 1.5 gram of nano clay, and then the clay has been mixed with epoxy, like that. So we took 3 different weight percentage of clay to fabricate the nano composite samples. So again, we use mechanical stirrer to disperse the nano clay with epoxy. Again, we have done some optimization about the spindle type and the time, the dispersion time, and then the speed of the spindle, like that. We have optimized the parameters, and then we were able to disperse the nano clay in epoxy matrix. And also we used ultrasonicator for secondary dispersion. But during this dispersion, we had a challenge, because we know epoxy is a viscous liquid. So we faced a lot of challenges in dispersing this clay in this viscous liquid, but somehow we achieved with good dispersion. So yeah, now so far I have talked about the preparation of nanocomposite. Now let us move on to microstructural characterization. So now it is very important to understand how the clay has been dispersed in epoxy. It is very important, right? Because as I told earlier, we are working in nano level, right? We cannot see the dispersion in our naked using our naked eye. So we need to go for some high funder tools to understand the dispersion of nano clay in the epoxy matrix. So for that, we have employed many techniques like X-ray diffraction. We have used scanning electron microscopy. We have used transmission electron microscopy. We have used laser-induced background spectroscopy, and also we have used some other techniques to understand the dispersion of nano clay in epoxy matrix. So this slide shows the wide-angle X-ray scattering. So you can see the black line shows the raw clay, which is the clay is in undispersed phase, and this brown shows a neat epoxy without clay. Only we took the clay sample, the epoxy sample, and we have done this X-ray scattering. And then this blue shows 1.5%, and then 3.5. So here you can see the observation of peak. You can see at D001. This corresponds to the integrated structure. So if you observe carefully, maybe I can zoom it. If you observe carefully, we do not see any peak for 1.58% clay. That means 1.58% clay provide good dispersion. So this is what we understand from this wide angle X-ray scattering. So the absence of peak at 1.58% clay content indicate exfoliation structure. So as I told earlier, the exfoliation indicates random dispersion of clay in epoxy. Okay, so this is what we understood from the wide angle X-ray scattering, and also we yeah. So here you can see So here I have given the pictorial representation of a different structure. So you can see the integral structure. We do not see a good dispersion. The clay has been arranged in some parallel fashion. It's in bit agglomerated stage, wherein if you see this right hand side, this extracted structure, the clay has been dispersed randomly. So this is what we want, and this dispersion we have achieved at lower clay loading, say 1.58% clay loading. So here I just wanted to show the different magnification of raw clay. So this left hand side micrograph shows low magnification. So it is around at 23,000 x. You can see it is an agglomerated state, wherein the right hand side shows higher magnification of nano clay, around 60,000 x. So this was taken using a scanning electron microscopy. And also we have done the small angle X-ray scattering. If you see in wide angle scattering, the angle is from 0 to 40 degree, but we wanted to focus only at small angles. So because we know that the D001 peak will correspond to the integral structure, so we wanted to focus at smaller angles. So that is why we have done small angle X-ray scattering. So from 0 to 10 degree. So again we observe the same. So the black shows the agglomerated clay, raw clay, and the red line shows 1.5%, where we do not find any peak. So this shows that that 1.5% has good dispersion, wherein 3 and 5 show a peak. So where the dispersion is integrated. So here you can see the transmission electron microscopy. So in the last figure I have shown the scanning electron microscopy. So where the microscopy is scanning, the micrograph was taken at the surface level, wherein in transmission electron microscopy TEM, the electrons will transmit through the sample. So this is the transmission electron microscopy images of 1.5% clay and 5%. You can see for 1.5%, you can see there is a random dispersion. But when you see for 5%, it has been agglomerated. So this what, so we have understood the dispersion of clay using different techniques from wide angle X-ray scattering, from small angle X-ray scattering, and also from TEM, transmission electron microscopy. So we wanted to understand the composition of nano clay. So it is the this is EDX. This has been coupled with scanning electron microscopy. So this is energy dispersive spectroscopy. So you can see the clay has silica, alumina, and magnesium. So these are the major composition of clay, which we all know. And also we employed laser-induced vectron spectroscopy. This equipment is available in IIT Madras with the Professor Nilesh J. Vasa. So just we send laser energy on the sample, and we understood the different composition in epoxy. So if you see the black line, the continuous line shows epoxy, which has only hydrocarbons. So epoxy has only hydrocarbons. But when we tested for 5% clay sample, we can see magnesium, silica, and aluminum. So this is what we understand from the composition, from the qualitative analysis of nano clay. So using SEM and scanning electron microscopy and laser-induced vectron spectroscopy. And again, we wanted to understand the energy required for laser plume. So just we did a little work on this area. So we took the epoxy and glass epoxy. Yes. Shall I continue? Yeah. Fine. Thank you. Yeah. So far we have been discussing about the calculation of nanocomposite to understand the dispersion of the nanoclay in epoxy. And also we have seen the qualitative analysis of nanoclay using two different techniques. So here just I wanted to focus on energy required for laser plume for different of epoxy and glass epoxy composite. Here by seeing the graph one can understand. See, this black shows the epoxy sample. So without clay, we require at least 12 millijoules of I'm sorry, I think it should be 5 millijoules. Yeah, so we required 5 millijoules of energy for laser plume for neat epoxy. For 1.5 weight percentage, we require more energy. It's around C5.4. And similarly, higher the clay content, we need higher energy. So this is what we understand from this graph. And the same trend we observe for glass epoxy composites. So the blue shows the glass epoxy, again 0, 1.5, 3 and 5. You can see for neat glass epoxy without clay, we need 12 millijoules. Wherein for 1.5 we need high energy, 12.6. So the idea is the addition of the clay in epoxy and glass epoxy lead to higher consumption of energy to produce laser plume. Fine. So now let us focus on the mechanical characterization. So far we have discussed about the microstructural characterization. So now let us come to the mechanical characterization of nanocomposites. So how are we going to characterize the mechanical performance of nanocomposites? So using different techniques, tensile testing, structural testing, impact testing, hardness, like that. So I'm going to brief each testing one by one, and also I'm going to mention about the standard which we have used. So for tensile testing sample, we used a dog bone sample as per ASTM D638. We have done the testing using a universal testing machine. So we used a dog bone shaped sample. I hope many of you are aware about the dog bone size sample. So this is the dog bone sample which we used, which we used to understand the tensile behavior. Okay. So I hope you agree with me. The purpose of having larger area is to avoid stress concentration, because this grip area will be rigidly fixed in the tensile. So in order to avoid grip failure, we have higher surface area, and also if you have sharp corner, then this will lead to stress concentration. That's why we go for this a curvature, so that we can expect the failure should happen at the cage length, so that I will get acute results. So that's why we go for dog bone size sample. So this has ASTM standard, D638 standard, and this is the response we get from the tensile testing. So as clay is a brittle material, so we expect when we disperse clay with epoxy, we expect a drop in the ductility. So this is what we observe, and also the same observation was observed by many researchers. And here I have presented the effect of clay and tensile modulus. So the addition of clay in epoxy leads to good improvement in the tensile modulus because of its good dispersion and because of its good interfacial addition between the nanoparticles and the epoxy matrix. And then structural testing, again we used a small beam samples as per ASTM D790, and we use a 3-point bending configuration. So you all know 3-point bending configuration. So it is supported on two supports, and the loading will be acting at the middle of the beam. So this is a typical 3-point bending configuration. So effect of clay and structural properties. So again, as similar to tensile properties, we have found improvement in flexure modulus by addition of clay, and also we have found good improvement in flexure strength also. But one drawback is we have found voids at higher clay content. So this voids lead to premature failure. And then we have done impact testing as per ASTM standard D256. This is the sample dimension. And again, we have got good improvement in impact strength by addition of clay in epoxy. Again, as I told earlier, at higher clay loading, because of this agglomeration and voids, we could not achieve good improvement for higher clay loading samples. And then also barcode hardness, as per again was done as per the ASTM standard D2583. So the hardness again shows improvement with increasing clay content. Yeah, here I have consulted the effect of clay and mechanical properties. So the addition of clay and epoxy lead to this much of improvement in 21% of improvement in modulus and 15% of improvement in strength, in resistance. Again, very good improvement in flexural modulus and around 22% of improvement in flexural strength, and again around 50% of. So this is a typical front surface of a epoxy. So this is the figure taken after the tensile failure. Just we took the failed sample to the SEM scan electron microscopy, and then we took this micrograph. So this shows a typical brittle failure. So we can observe from this micrograph. And also we wanted to understand the clay in glass epoxy. As I told earlier in my previous slides, I was mentioning in the whole talk we use two materials. One is polymer nanocomposites, where we disperse the clay in epoxy and we understand its mechanical performance. And the second one, we wanted to understand the effect of clay in a traditional composite. You know a composite, right? FRP is the composite where the fiber is the reinforced, is the major reinforced, is the primary reinforcement, and the polymer is the matrix. So in a traditional composite material, we have added that nano clay, and also we have found a good improvement. So here I have listed out the improvement of mechanical properties when we disperse clay in glass epoxy composite. So again, this is the photograph of fiber reinforced composite. You can see by addition of clay in matrix, you can see very good bonding between the matrix and the fiber. So this bonding lead to better performance in mechanical properties. So this is what we understand the effect of clay in general composite, glass epoxy composite. And one more thing I want to have a I want to emphasize on this data. One can observe there is a limited improvement in tensile properties, but there is a major improvement in this intralaminar shear strength and impact strength. The reason is these tensile properties are dominated by the fiber, where the fiber will play a major role. The matrix may not play a major role. Wherein, if you see in this intralaminar shear strength or impact strength, here the matrix play a major role. So that's why we get a better improvement, because what we have done, the matrix has been dispersed with epoxy clay, right? The matrix epoxy has been dispersed with in clay. So that is why we could see good improvement in matrix dominant properties like impact strength and intralaminar shear strength. So, but we could not get good improvement done thermal stability. We wanted to understand the effect of clay on thermal stability. So again, we have found that the addition of clay in epoxy lead to better thermal stability. So we have got shift in the decomposition temperature. The addition of clay in epoxy, the decomposition temperature has been shifted to higher level. So this is what we observed from this thermal stability. So this test was done on thermogravimetric analyzer. So from this we observed that addition of clay lead to better thermal stability. Then also we were curious to understand the effect of clay on electrical properties. So we have done some work on electrical properties. So that is one is breakdown voltage. So the breakdown voltage is nothing but it is a property of insulator. We call it breakdown strength. So this from this test we observed that addition of clay lead to better breakdown strength. So one can observe. So the sample was subjected to high voltage, around 5 to 10 kV. So you can see the photograph after the application of electric voltage. So the neat sample, you can see there is here a major damage. So the for a sample having 1.5% clay with epoxy, you can have minimal damage. So the idea is by addition of clay in epoxy lead to better electrical properties. So this is what we observed from this breakdown voltage test. Now I have come to the important objective of today's talk. This 11. Okay, fine. So let me focus on this topic for a while. So the main objective of today's talk is to understand the high standard testing of composites. This was my primary objective. So why do we go for high standard testing? So this is this thing we have to answer. So why do we go for this testing? What is the necessity? So I have just listed out the reasons. In general, materials are sensitive strain rate. Okay, so like that, polymer composites also are very sensitive to strain rate. So that's why we need to understand the strain rate behavior. And also in practical applications, the composites will subject to high velocity dynamic loadings. So it is very important to understand its properties at dynamic loading. And also for development of numerical failure criteria, we need the properties at high strain rate. So that's why we have to understand the properties of composites at high strain rate. So we have done two different characterization. One is low strain rate and high strain rate. So I will explain the different types of strain rates in my next slides. So for low strain rate characterization, we have used universal testing machine, and we have taken we have done the characterization at different crash speed. So here I can give the strain, I can explain the strain rate. So this 0.5 mm per minute, this is the cross speed of the UTM machine. So this is the speed where I can pull my material. At this speed I can pull the material. So this so now this speed can be converted into strain rate. So I need to divide by the cage length. So when I divide by the cage length, I will get some value. So that value is called strain rate. So generally we indicate the strain rate in per second, 1 by second. Okay, so 0.5 mm per minute can be converted into 0.0 mm per second, and then this value has to be divided by the cage length. So and then I will get the strain rate. So to get different strain rate, to get different strain rate, we need to have different velocity, right? We need to have different cross speed. So we used instrument machine. So in that machine we can set the speed. So it varies from 0.5 to 1000 mm per minute. So we chose four different cross speeds: 0.5 mm per minute, 5, 50, 500. So generally we do at 5 mm per minute for quasi-static loading to understand the understand its mechanical properties. But here we have done a different velocities to understand the behavior of material at different strain rates. So this is the response. So one can see the difference in stress and strain at different strain rates. So 0.001, this corresponds to lowest strain rate. Maybe I can use the pen. So this corresponds to 0.5 mm per minute, wherein this 0.1 corresponds to 500 per mm per minute. So just we have taken 4 different strain rates, and that is 4 different crossed speed, and we wanted to understand its behavior. So you can see at a lowest strain rate 0.001 per second, we can see for neat epoxy, you can see the strength is around 40 megapascal. Now, when I do the testing at higher strain rate, at higher loading rate, you can see there is increase in the strength. And also, one can see there is a drastic increase in the slope also. So, the slope will give my Young's modulus. So, from this figure, one can understand the polymer is a rate sensitive. So, this is what we can understand from this figure. So, we have taken 4 different strain rates, loading rates. So, when we do this tensile testing at this strain rates, we could find the change in properties. So, we have found around 15% of increase in the tensile modulus from low to high strain rate. Again, we have found around 36% of increase in the tensile strength. You can observe here. See, at lowest strain rate, at 0.001 per second, we have got around 40 megapascal, wherein at the strain rate of 0.1 per second, that is at 500 mm per minute, we can see a strength of 655 megapascal. So this is what we understood. This is the behavior of the material. So from this we can see the epoxy is rate sensitive. But here we have focused only on low strain rates. Now let us focus on high strain rates. Let us focus on this area in my upcoming slides. So here I have plotted the effect of strain different clays for different samples. So this is the strain curve only for epoxy. So the same testing we have done for clay samples. So we observe the same trend. Similar to epoxy sample, we get the same trend for clay epoxy samples. So here I have given the results. So we have got increase in that the strength because of increase in the strain rate. Here I have given that the data for different samples, starting from epoxy to clay samples. Fine. So now we wanted to understand the rate sensitivity of a typical composite material. So now we have taken glass epoxy, where glass is my primary load carrying element and epoxy is a matrix. So we observe the same trend. So again, this 0.006, this corresponds to 0.5 mm per minute, and this corresponds to 500 mm per minute. And one can question me why the number is changing, because for epoxy samples I get 0.001, but for glass epoxy I'm getting 0.006. The reason is because the cage length of the sample is 50 mm, but here the cage length is I think 25 mm. So that's why we got we have changed in this data. Yeah. So here you can see the black shows the strain curve of your glass epoxy at the lowest strain rate 0.006 0.5 mm per minute, wherein this blue shows the strain curve of glass epoxy at higher strain rate, around 500 mm per minute. So you can see there is a drastic increase in the strength. So this is what we observe from glass epoxy composites. So this is the effect of clay on tensile properties. So this we have observed. So as I told earlier, there is a drop in ductility, there is improvement in stiffness, there is improvement in strength, and again these results which we got for glass epoxy clay composites. So we have found that our observation is both epoxy, glass epoxy, and both epoxy clay and glass epoxy clay composites are rate sensitive. This is what we observed from this study. Now, so far we have focused on low strain rate. So by using UTM, I can have different cassette speeds. I can do different strain rate. Now, how can I achieve higher strain rate? So again, there is a important thing, right? We need to discuss. So here I have listed out the different techniques for high strain rates. So for less than 0.1 per second, we can use conventional loading frame. For 0.1 to 100 per second, we can go for servo-hydraulic machine. And for 100 to 1000 per second, we can use drop mass setup. And for above 1000 per second, we can use split half-position pressure bar. For above 10 power 4 per second, we can go for expanding ring. So in this work, in this research work, in today's talk, I am going to focus on drop mass setup. So we have employed a drop mass setup to understand, to achieve high strain rates. And also we have found there is a gap in the literature. So people have focused on low temperature, low strain rate, people have focused on high strain rate. But we could not find enough literature on this intermediate strain rate, that is from 100 to 1000 per second. So that is why we have made an attempt to do the testing at this region. So for that, we have employed a drop mass setup that was indigenously designed and fabricated at IIT Madras. So, so today I'm going to share my results, which we have done experiments from this drop mass setup. So here again, there's I wanted to explain the different strain rate regime. So this is the 10.-3 is the region where we can say it's static loading, and 10⁻³ 10⁻² per second we say it's intermediate strain region. We can use servo-hydraulic machine, drop mass. So generally the plane crash, vehicle crash will subject to this kind of loading. So it is important to understand the properties of material at this regime. And again, for high strain rate, we go for split half-position pressure bar. Again, this is the range, 10⁻², 10⁻⁶, and again the application is ballasting and bullet impact. So the bullet impact structures will experience this strain rate. So we need to understand the properties of the material at this region. And for ultra high strain rates like nuclear explosion or astrophysical events, to achieve this ultra high strain rates, we go for Taylor impact or plate impact. So this is the some basic idea about different strain rate regime, and what are the techniques available for achieving the strain rates and what are its applications. So in today's talk, I'm going to focus on this regime, that is intermediate strain rate. So for that, I'm going to, we have used a drop mass setup. So I'm going to focus on this area. Fine. Now, so here I have given the drop mass setup details. So what is the advantage of drop mass setup? So we can achieve intermediate strain. We can achieve intermediate strain rate from 10 to 1000 per second, and it's inexpensive. It can accommodate different geometries, and also we can it provides easy variation of strain rate. So this is a typical photograph of a drop mass setup. So now one can understand just by dropping the mass, we can achieve different velocity. We all know, right, from law of conservation of energy, we can say the velocity is equal to V is equal to root of 2gh, right? So when I change the height, then I can change the velocity also. So this is the basic principle. So based on this principle, we achieve different velocity. So different velocity lead to different strain rate. So we chose 3 different heights, say 0.5 meter, 1 meter, 2 meter, like that. So by dropping the mass at different height, we get different velocity. So different velocity will lead to different strain rate. So as I told you earlier, the strain rate is nothing but the velocity to the cage length. Velocity to the cage length. So this is the strain rate. So this is what we achieved by using this drop mass setup. Fine. Now we need to focus on the fixture. So now now we have identified equipment to achieve high different velocity. By dropping the mass at different height, we can have different velocity. Now the main challenging task is how am I going to fix the sample? How am I going to extract the data? It is a very important thing, right? So for that we have designed a picture. So this picture, the whole picture and the setup has been patented. It has been published, and we are able to get the grant. So here you can see it has a mobile jaw. So the sample has been fixed here. So when the mass hits here, maybe I can show using a pen. When a mass hits here, when the drop mass hits this picture, then the sample will experience tensile loading. So that the sample will experience tensile load, and it will lead to failure. So now the tensile load can be extracted from the load sensor, which has been mounted at this point. So this is the principle. From this idea, we achieved a high strain rate, and also we designed a fixture to load the sample at high strain rate, and we use a load sensor to record the load data. So this figure shows the specimen picture, how the sample has been mounted in this drop mass setup. Now let me come to the important topic. As I was telling in my first slide in the roadmap of today's talk, I was mentioning DIC, digital image correlation technique, and I was telling about the non-contact strain measurement technique. So I'm going to take 5 minutes and explain this topic. Organizer, shall I proceed? Do I have time? Enough time? Moderator? Moderator, can you?
Yes, sir.
Yeah, am I audible?
Yes, yes, sir.
Am I allowed to speak for another 10-15 minutes?
Yes, sir. Yes, sir. You are free to talk. Since
yeah. Thank you.
Open till 12 p.m.
Fine. Okay, fine. Thanks for the note. Okay. Let me proceed. Yeah. So in the beginning of my talk, I was telling about this DIC. So digital image correlation technique. And also I told it's a non-contact measurement technique. So I'm going to focus on this topic for a while. In general, we use extensometer, right, to get the strain data. We have used in our laboratory Synthomidis laboratory, we use extrusometer, and using extrusometer we get the strain data. But the strain data gives strain between 2 points, right? Generally, based on the cage length of the strain data, of the cage length of the sensometer, we get strain between 2 points. And also we use the strain gauge, right, to get the strain data. We used to bond the strain gauge on the sample and we apply a load, and using which Visual circuit we get the strain data. But the strain data will give strain over a small area, right? But with DAC, the technique which I am going to explain today is a technique which provides full field strain data. That is its significance. So by using extrusometer, we get strain between 2 points. By using a strain gauge, we get strain data over a small area. But with the help of DAC system, it is possible to get the strain data for the whole field or the full field strain data. So this is a technique which we have employed to get the strain data. So in my previous thing, in this top setup, I was telling you how to achieve different strain rates. So I have told that by changing the mass, height, we can have different velocity, and also we use load sensor to get the load data. So for strain data, we use this DH technique. For getting the strain data, we use DH technique. It's a non-contact strain measurement technique that we will discuss in my next slides. So because to draw a strain diagram, I need to have load data, I need to have strain data, right? So the stress data can be taken from the load sensor, and the strain data can be taken from this DAC system. So this is what we have used in this research work. Fine. So now application of DAC. I want to give you a quick idea about the applications. Because as I told earlier, this DAC is a full field strain technique. I can get the strain data over the entire sample surface. So it is being used in fluid mechanics to measure the velocity fields, and we can use the DAC in thin films because we know it is difficult to test a thin film, because it is difficult to use extrusometer strain gauge for thin film, right? So with the help of DAC, we can measure strains from thin films, and we can use DAC to measure the strain field near crack tip. In fracture mechanics, we know at crack tip we experience a large strain. So to understand the strain field at the crack tip, we can go for DAC, and also we can use DAC for crack tip opening displacement, and also we use DAC in concrete. In concrete also we use DAC to get strain data. So like that, it has a wide range of application, and also it is a non-contact measurement technique. Okay, so this is what about the application of DAC. Now let me show the DAC process. So it has 3 processes. First, you need to prepare the sample. You need to make a speckle pattern, and you need to record the images before and after the loading until the failure. So we need to use a camera. So by using a camera, CCD camera, we can record the images, and then post processing the images using algorithm. So these are the 3 main steps in DAC process. By following these 3 steps, we can get the full field strain data of a material. So this is a DAC setup. So here you can see this sample is being subjected to tensile load, and lights have been kept for better illumination, and a camera has been set. So we'll take a reference image, and then while loading, we have to record the images till the failure point. So once the images have been recorded, then we can do the post processing, and then we can understand the strain variation along the surface of this material. So this is the the sample which we have used for this high strength testing. Based on the literature survey, we have chosen this sample. It is a 3 mm width and 10 mm cage length, and here we have taken the spectral pattern. So this is a spectral pattern. So this is the important step in DIC. Sample dimension, distance between the camera and sample, and focal length of the lens, light source, spectral pattern. How am I going to make the spectral pattern? And then type of algorithm. So like that, many parameters we have to make to get a better results. Yeah, here I think this figure shows the importance of DIC technique. So we can see the full strain field. As I told earlier, if I use extensometer, I will get strain between 2 points. Maybe I get strain between these 2 points. If I put extensometer, maybe I get strain between these 2 points based on the cage length of the extensometer. When I use a strain gauge, I will be getting strain over a small area. So based on the size of the strain, strain gauge, I will get the strain over a small area. But with the help of this DIC, it is possible to get the strain over the entire surface, or I can say full field strain data. So this is what we get from the DIC technique. So here I have plotted the stress strain curve of a epoxy clay sample at high strain rate. So you can see here this black shows the quadratic data which has been done at quadratic loading, and this is the red shows the tensile stress strain curve at high strain rate. So this is the strain rate we achieved by using drop mass setup 385 per second. So you can see we can see the strain contour at different time step. So at beginning you can see there is a strain localization, again there is increase in strain, and then you can see a drastic increase in strain localization around 530 microsecond, and then the sample lead to failure. So from this DIC technique we got the strain data, and also from the load sensor we got the stress data. So with this idea, we were able to get the tensile stress strain curve for epoxy samples at high strain rates. So here I have shown the effect of strain rate and modulus. So this whole data which was done at quadratic loading for different clay samples, neat epoxy to 5 weight percentage clay sample, and this is at high strain rate. So here I have shown the enlarged view. So as I told earlier, we took 3 different height. So we got 3 different velocity. So 3 different velocity of C at 315 per second, and this is at 385 and 450. So there is increase in the modulus value, and the same trend has been observed for clay samples. You can see this red shows for clay sample 1.5%, and the green shows modulus for 3 weight percentage. So like that we can see the metal is highly rate sensitive, and this figure shows
তোমরা হচ্ছে আপনি হোয়াটসঅ্যাপে গ্রুপ ফর্ম করো, তোমরা একদিকে এসো, তোমরা কলেজে এসো শোনো তোমরা কি
স্যার 1 মিনিট
তোমরা কি ভাবছো না ভাবছো সেগুলো তো একটা ভাইবার আলোচনা করার সময় নয়।
মিস্টার নির্ভিক ব্যানার্জি, ক্যান ইউ মিউট ইউর মাইক প্লিজ?
তোমরা কেমন পথে এগোবে সেটা তোমরা আমার সাথে যদি না দেখা করো বা মানে গুগল
স্যার, let me mute him. Yeah, it's done, sir. You may proceed, sir. Sorry for that.
Thank you, sir. So here this data shows two important understanding. See, one, you can see the modulus are increasing with respect to strain rate. You can see that we can say that the metal is rate sensitive. This is the one data we can observe from this graph. And one more data, we can see there is increase in modulus by addition of clay. You can see at for neat epoxy we got around 5 gigapascal. wherein for 1.5 percentage we got around 5.5. For 3 we have got 6.5 gigapascal, and for 5 percentage we have got 7 gigapascal. So we can interpret this data in two ways. One, the addition of clay lead to increase in tensile modulus, number one, which we can observe at all strain rates, at quadratic, at high strain rates, which we can see. You can see here there is increase in the modulus by adding clay epoxy at all strain rates. And second interpretation, we can see the material is rate sensitive. So at quadratic, we have got 3.5 gigapascal as the modulus for neat epoxy, wherein when you do the testing at high strain rate, the modulus has been increased from 3.5 to 5 gigapascal for neat epoxy. You see the black one. And similarly, when increases strain rate to 315, from 315 to 385, there is increase around 5.5. Now, further increase in the strain rate lead to again increase in the modulus around 6 gigapascal. So this is what we observe from this graph. So this trend has been followed for other samples also. And this figure shows the scanning electron microscope photography at quadratic loading. So this is for neat sample. You can see it is we can see a featureless image, the river-like pattern, which we observe for a brittle failure. And this is for again 1.58% clay. You can see there is the agglomeration, and also you can see the roughness also increased, which provide which shows that the brittleness has been increased. So this is what we observe from this micrograph. And again, this figure shows the effect of standard strength. In the previous slide, I was focusing on modulus, tensile modulus. So the left hand, the y-axis was tensile modulus. Now I wanted to focus on strength. So here you can see this the variation of strength at different strain rates and at different clay loading. So you can see here one can observe that the strength of higher clay loading is not good. You can see here the blue shows the 5% clay loading, but it is we may end up with micro voids. So this micro voids lead to premature failure. So that is why the improvement of strength for higher clay loading is limited. But at the same time, we have got good improvement for lower clay loading. You can see, you can observe here. Maybe you can zoom it. See, at this figure, you can see black shows epoxy. So we have 40 megapascal as the strength, wherein this red shows the 1.5. We have got 50 megapascal. So there is improvement from 40 to 50. Again, for 3%, the green is showing 55. But again, this blue, we are supposed to have get good improvement, but we could not because of that micro voids. So this is what we observe for different epoxy clay samples, and the same trend has been followed for other strain rates. You can see the same trend has been followed. So again, this figure shows that confirmation of micro voids at higher clay loading, and this figure shows the micrograph at higher strain rate. So you can see the micrograph has rough surface. So the material, the brittleness of material has increased. So this is what we observe from this micrograph. So again, this is the effect of strain rate on glass fiber epoxy clay. So far I have focused on epoxy and clay alone. Just we did explanation only on epoxy and clay nanocomposites. Now here we wanted to focus on glass epoxy fiber reinforced composite with clay. So here you can see we observe the same trend. For quadratic, we have got around 300 megapascal as strength, but when I do the testing at high strain rate, there is a drastic change in the strength and stiffness. You can see the slope. You have a very steep slope. So this slope indicates the stiffness of the composite or modulus of the composite. And this is the DAC counterplot. So just before the failure. So you can see with the help of DAC, we can have full field strain data. You can see there is a strain localization at the middle of the sample. So further loading lead to the failure. So here you can see the you can see the failure of the sample. So the sample was failed at 1460 microsecond. So we used high-speed camera to capture images, because you all know, right? The loading happens in microsecond. So I cannot use a normal camera, right? So I need to use high-speed camera so that I can have image for every 10 or 1 microsecond. So with the help of high-speed camera, we were able to get images at every 10 microsecond, and then we did the post processing of the images, and then we got this the strain contour plot. So with the help of the strain data, we could plot the sustained curve of the sample at high strain rate. Yeah. So now I have come to the end of my talk. 11:50. Anyway, as I was telling in my previous slides, that we use Kalski bar to achieve very high strain rates. So this is the typical representation of a option pressure bar. So it works on one-dimensional wave propagation. So just I have given that the schematic of that pressure bar setup. So here, when the second bar hits the incident bar, then a stress wave will be generated. So this stress wave will propagate through this incident bar. So so now when the incident bar hits the sample, then the sample will load at high strain rate. So anyway, I don't want to get into this business because it's out of the scope of today's talk. I just want to show the schematic of option pressure bar. Here you can see the signals from that setup. Yeah. So now let me quickly come to the end of my talk. So here this figure shows the micrograph of neat epoxy, different magnification. So you can see smooth, glassy, featureless fracture surface, which indicates a typical brittle fracture behavior. And like epoxy clay, we can see there is agglomeration and deep river markings, and this, and also we can see this surface roughness is increased, which confirms the clay particles. And again, this is the figure of clay epoxy at higher strain rate. Again, this is the figure for glass epoxy clay. You can see this is the you can see poor bonding between matrix and fiber for neat epoxy, but we could see good bonding for clay epoxy samples. So because of clay addition, we were able to get better bonding with the fiber. So this what we can observe from this micrograph. Again, this figure shows fiber breakage and debonding at high strain rates. Yeah, so these are my concluding remarks. So the concluding remarks are: so we have observed that addition of clay in epoxy in polymer and the composite lead to good improvement in mechanical, thermal, and electrical properties. And we have successfully employed drop mass setup to achieve intermediate strain rates. And we have found that DAC is highly compatible with the drop mass setup to get reliable strain data. So this is what we have discussed in. Also, we have found that the tensile properties of both epoxy and glass epoxy composites are rate sensitive. So the future scope is we can explore a lot on understanding the mechanism of nanostructure, so that we can get better engineering properties, and also we can focus on the design and development of test standards. We don't have such standards for high standard testing. We have standards for quadratic loading, but we don't have standards for high strength testing, so that we can also focus on this area. We can develop standards for high standard testing. And I would like to acknowledge my guide, Professor Velmurugan of IIT Madras. And I would like to acknowledge Professor Sarathi Group for doing electrical work at his lab. And also I would like to thank and acknowledge Professor Nilesh J. Vasa of IIT Madras, who helped me to do testing on laser-induced background spectroscopy. Thank you very much for your kind patience. So, if you have any questions, please feel free to ask.
Hi, sir.
Thank you, sir. Thank you for your wonderful session. We are very happy to have you here. Now, I may request the fellow participants to raise your questions either by unmuting your mic or by posting your questions in the chat box. Actually, we have already some set of questions from the participants. Sir, do you want me to read it out for you, or else shall I ask them to unmute the mic? Sir?
Yeah, I can see the questions. Maybe
Okay,
let me go through one by one.
Okay, sir. Questions from Dr. Piyush Gar.
Yeah.
1 minute, sir. Excuse me. Mr. Derishan Fernando, can you wait for a moment? Let the speaker complete the answers for the previous questions, and then he will come back to you for sure. Yes,
Yeah.
sir. You may go ahead, sir.
Yeah. There was a question by Dr. Piyush. Did you work in developing nanocomposites for ballistic applications?
Good afternoon, sir. This is Dr. Piyush.
Yeah. Good afternoon, sir. Good afternoon.
Yes, sir. Good afternoon. Yeah. I have few set of questions actually. I wanted to ask. It was a very interesting work to see the effect of nano clay.
Yeah.
So I actually worked in the area of ballistics and developing the materials for impact and blast actually. So I was just wondering, like, have developing nanocomposites for ballistic applications or not?
Yeah. Actually, we have not focused on nanocomposites for ballistic application, but our main objective was to understand its property at high standard. But still, our laboratory, our group worked on ballistic application, and also I could see people are working on nano layering concept. So instead of going nano composites, they use a nano layer, kind of nano coating. So that by having a nano coating, it is we can achieve a good ballistic performance. So many work is going on this area, but I can say nanocomposites are being used for ballistic applications. So many researchers are working on that.
And sir, regarding one thing you have mentioned in the experimentation while you were preparing the while you were explaining about the fabricating of the nano composites, I just wanted to ask, you have mentioned about ultrasonification, right?
Yeah.
Like when we actually dig the solution in, when we dig the nano clay into the epoxy with the help of a mechanical system. Two set of questions I have. What is the RPM of the motor that you have used for mechanical stirring, and what is the frequency you have used in dispersing the clay into the epoxy while doing ultrasonification? So is there some suitable standard for that?
Yeah. See, actually, the dispersion of clay in epoxy is very, very important to achieve good properties. So we spent a lot of time in choosing the parameters, like the type of spindle, what kind of spindle we have to use, and the speed of the stirrer. So because again, when compared to other polymers, epoxy is a bit viscous fluid. So again, we had challenges in mixing the nanoparticle in a viscous liquid. So we have done some homework on this different RPM, and then we found around 2000 RPM. That is the optimal speed, and also we have also done some experiments on timing. How much duration we have to disperse the clay in epoxy. So based on different experiments, we optimize that the parameters, the speed of the spindle.
What is the time required for like
Yeah,
mixing?
to get good dispersion, we need to we need to disperse for 4 hours.
Oh,
We have
4 hours
found,
continuously,
yeah,
sir.
yeah, 2 to
Okay,
4,
okay.
yeah.
So is the nanoclay gives the same problem? Like, is it it is very hard to mix silica also into the silica, especially at the higher ratios. It gives the same problem of agglomeration of what you have mentioned about the nanoclay. So
Correct.
that is the reason I was asking actually, what is the frequency of ultrasonification that you have done actually? I'm just asking for the improvement of my work. So
Okay,
that is why
okay.
I'm actually asking about all these things.
That
Yeah.
frequency, I currently could not recall, but the purpose of ultrasonic is to, because the primary dispersion was done by, was carried out by mechanical. But for higher clay loading, when we go for higher loading, say 3 or
Yes,
5
yes.
percentage, we need to have secondary dispersion. So that is why we had to go for ultrasonicator. Uh, I will try to recall that frequency. I'm unable to recall now.
Sir, just I'm sorry. Is it in kilohertz? Any idea? Is it is in kilohertz or in megahertz? Just to have an idea, actually, I really want this help. So, was it in megahertz or was it in kilohertz, or how many cycles of ultrasonification you have done
Actually,
during that time?
we used the ultrasonic cleaner. We It is commercially available. With that ultrasonic cleaner, we pour the water, and then in that bath we kept our the clay sample.
For how many minutes or hours you have kept there?
For 10 to 15 minutes, we kept it ultrasonic cleaner.
Okay, you may. Okay, okay, fine. I think 10 to 15 minutes is the standard, right?
Yeah, yes, yes,
Okay,
yes.
okay. So, sir, it is actually clear from your PPT that nanoclay gives don't give that much improvement in impact properties. So, for ballistic material, it will not be recommended. So, actually, I am also I am also investigating many nanofillers,
Yeah,
especially in the Kevlar materials. So,
correct,
what I find out is that nanoclay, in my studies, I found out nanoclay is not giving good impact properties.
correct. Because of
So,
its brittleness.
yes, yes, yes. Your results definitely agreed with my results also. Sir, another question I have is asking you about, since it is a fibrous material,
Hmm.
you have taken glass fibers and all. Don't you think that using dog bone shaped specimen as per standard of what is 863 standard you have used, right? What is the
Yeah.
standard you have used?
No, for polymer, it's D that we have used for polymers,
So,
dog bone shape.
yeah, don't you
Uh,
think that it will affect the fiber continuity in one direction using
no, no,
dog
no,
bone
no, no, no,
specimen?
no, no. For fibers fiber samples, we have not used dog bone. We have used D3039.
Okay, okay,
Rectangular samples. You are right,
okay.
because we cannot use dog bone for fiber composites, but we used dog bone samples for polymer composites, not for fiber composites.
Sorry, one question out of my curiosity.
Yeah, please.
Like I have worked a lot in extended testing of human body tissues also
Oh, good.
for impact applications. I just wanted to ask, can we use the same shape of specimens for like ASTM 3039 or D863 for soft tissue tensile testing, especially at higher standards? Because for testing the tissues in tensile loading, there is no standard.
Correct. I agree
So,
with you. Yes, yes.
can this be applicable onto the soft tissues, soft fibrous tissues also?
Again, we have to look into the literature. But it can be. We can
I'm,
apply the
I'm
standard for. We
My
can still.
apologies for asking so many questions. I really
Yeah,
want
yeah.
to clear my doubts also.
Fine,
So,
fine.
sir, last question I just wanted to ask: what were the DIC patterns that you were showing, especially the strain pattern? So, did you use I'm sorry, it was a hello. Yeah, am I audible?
Yeah, I think you're back, sir.
Yeah, I am sorry.
I don't know.
I'm,
It has actually
I'm sorry. I'm sorry.
it has sent me automatically to some other break
Yeah,
break room and
yeah.
all.
The same thing I
Yeah.
also had. I'm sorry for that.
Yeah,
Yeah,
it's okay, sir.
Dr.
My
Piyush, you
apologies.
can continue. You are asking about some DAC questions. Kindly.
Yeah, sir, I just wanted to ask last question only.
Yeah,
Which was
please.
that DIC software you used? Was it a open source Encore or some
No,
other?
no. We have used with 2D. We have bought the software. Though there are many open source softwares are available, but again,
Okay.
it has a limited limited version. So that's why we went for commercial package software with 2D, so that we can have in-depth analysis on this DAC, on this DAC data. So we used with 2D.
And
With
which
2D
ink
software.
which ink you have used for the speckle patterns? To draw the
Again, yeah, again, see, generally people use paint, use spray paint. They make a white paint to have uniform thing, and then they use black or blue paint to have the speckle pattern. But again, in this DS technique, I have mentioned in my talk that we used high-speed camera. So high-speed camera, the resolution of high-speed camera is very limited. It's 1 megapixel. So when I make a speckle pattern using paint, it will be difficult for me to capture that fine speckle pattern. So the paint may not work for this application. That is why we chose a manual. We chose a marker, current marker. Using that marker, we made the speckle pattern so that we could achieve good results. Because
and
if we go for fine speckle pattern, then we may not end up with good correlation.
there will be definitely pixel distortions actually.
Correct.
Because the lesser the size of the pixels, more the distortion will be. Yes, sir. What was the frame rate you have used for drop down
Yeah,
testing?
I mentioned right. We worked at 1 lakh frame per second, so that for every 10 microsecond, I get one image.
Okay. 1 lakh is too much actually.
Because no, by 1 lakh only we can achieve at least 10 data. See, if you see if you see the load time diagram, the load time load versus time plot, the failure will happen in 250 microseconds.
Yes.
So that's why we set it to 1 lakh frame per second, so that I will be getting one image at every 10 microseconds, so that I will be having at least 25 data points to plot the sustain curve. But it will be nice. It will be nice if we go for higher frame rate. But again, because of some constraints, we could not go higher than above 1 lakh frame per second.
So did you synchronize your deck and camera?
Yeah, yeah.
Okay, thank you, sir.
Thank you, Dr. Piyush, for your interesting questions. Thank you.
No problem, sir. Thank you.
Thank you, sir. Is there any other questions from the participant side? You may please unmute your mic, or else you can post the questions in the chat box.
So, Tamil Vendan, there was a question whether I have used pristine clay or modified clay. So, for our research work, we have used modified clay, because the pristine clay or the unmodified clay, if you use with the clay, we may not get good dispersion with epoxy, and also the clay may not miscible with the fiber. So that is why the clay has been modified, and we have used modified clay for research work. So I had a question about what kind of clay I have used for my research work, whether unmodified or modified. The answer is we have used modified clay.
Hello, sir.
Yeah. Yes, sir.
Sir, three things very clearly. One thing is your comment on crystallization and give more detail. One can use the still very hard nano composites in that.
Sir, I am sorry. I was.
Sir, I think your voice is breaking, sir.
Yeah, hear properly.
Voice is breaking.
Your voice
should I repeat it, sir, once again?
Yeah, please. Please.
Sir, your comments on crystallization, and can we use much harder nano clay material? And the third one, more detail about the CCD camera.
Okay. Okay, fine, sir. I got. Yeah, crystallization. Sorry, I have not opened this area. I am unable to comment on this area. Coming to clay, clay again. This clay has been used by many researchers, especially in this past 2 decades. So we have many numbers of commercial clay available in market. So based on our requirement, we can go with the commercial clay. And the third thing about CCD camera. So again the camera also we need to pick the camera based on our requirement. For example, if we go for say quadratic loading, so for that a 50 fps normal CCD camera is sufficient to carry out the DAC testing, and we get the strain data. For example, if I go for high standard loading, if my loading rate is higher, then the normal CCD camera may not work. For that, we need to go for high speed camera. So generally, high speed camera comes in CMOS type. So generally, high speed cameras they go for CMOS. High speed cameras we don't have high speed CCD cameras. So based on our requirement, we need to choose the camera. Again also the FPS, the frame per second also play a major role in getting the accurate strain data.
Yes, sir. Thank you. Any other questions from the participants? Please, Mr. Natraj MV, I think he has raised some question.
Sir, good afternoon.
Good afternoon.
Is it audible, sir?
Yeah, you are audible.
Sir, good afternoon.
Yeah, you are audible. Please go ahead.
Thank you, sir. Thank you, sir. It's a very nice and informative session, sir. It's very interesting also. And even I worked with multi-wall carbon nanotubes in polymer composites during my MTech time. Now I am doing PhD in metals. And my question is relevant to the high strain rate process, sir. Generally, high strain rate means what exactly it is like? It is applied load versus time, or else something else?
Exactly. See, it is about the loading rate, at how fast we are applying the load. In our typical testing to get the mechanical properties, we do at quadratic loading, say 0.5 to 5 mm per minute. So we used to pull the sample at a quadratic speed. But when high strain rate, the sample will be loaded at high velocity. So this was high strain rate. But why do we want to go by strain? That's the question. The reason is, in general, the materials are sensitive to high strain rate. For example, when I pull the sample at a low strain rate, I get some properties. But when I pull the sample at high velocity, then I will end up with some other properties. So we need to understand its behavior at different strain rates, and also in practical applications. Example, I can give example of a bird may hit the flight. So the flight is flying at a high velocity. So the bird may hit at high velocity. So now at this junction, the material may experience high strain rate. So that is why we need to understand its behavior. So that is why what we are doing, we are replicating that action in our lab. So we are trying to understand the property at that strain rate, at that type of loading. So that is why we go for high strain rate.
Yes, sir. Generally, the definition wise and the statement wise, people used to say rate of deformation is nothing but as high strain.
Yeah. Again, for metals we use deformation. Again, composites we generally we don't use the word deformation because the composites may not go for plastic. Means when compared to metals, that is why we don't use use the word deformation. But yeah, as you told, high strain rate is nothing but it's the loading rate. At what loading rate I'm doing the testing.
Sir. Thank you, sir. And even I understand the same thing only. It is like load versus time.
Correct. Yeah.
As you said, like, thank you so much, sir.
Yeah.
And even I also worked with SHPB. They'll use different pressures, actually pressure bar it is.
Correct. So in drop mass setup, I mentioned that by changing the mass, drop mass height, we can get different velocity. The same idea we use in pressure bar, but there we have to change the pressure. So higher the pressure, higher the velocity, higher the strain rate.
Sir.
So,
And last question, sir.
Yeah,
and
please.
even I posted in the text also, so in SSPB, so as you shown one graph also.
Yeah.
So how to do? I mean, sir. So in one slide you have shown that last before a couple of three slides.
Actually, I worked on this area during my postdoc tenure. Actually,
Okay.
I just wanted to focus on that because I was telling all different types of strain rate regions. I was telling different types of techniques. So that's why I just wanted to focus how what is the principle of option pressure bar. Again, that graph that was a data of a ultra high performance concrete. Again, the data was taken from a strain gauge. So in split compression pressure bar, we use the strain gauges. One is incident signal, incident bar, and transmitted bar. So we used to paste a strain gauge on both bars. So the incident signal will give the stress wave, what the incoming, what is the impact energy, and the transmitted signal will give the stress wave. Again, the referred signal will give the strain rate. So again, it's totally a different thing. But the data I have shown the raw data. So that signal which I have shown is it's a typical raw data of a ultra high performance concrete tested using split option pressure bar. So they are incident signal and transmit signals. So from that we can get the strain data, and from that we can get the strain rate also.
Okay.
So yeah.
Sir, thank you so much, sir. And even SSBB is also, the strain rate is 10 to 10 power 3 per second, I think, 10 power 3 to 10 power 4 per second, I guess.
Correct.
So with that impact load, so how this polymer composite really reacts, so is one of the nice thing only, sir.
Fine. No, the people have worked a lot in this area. Though I have focused only on intermediate strain rate, but if you see literature, many researchers have worked on this high strain rate. They have used option pressure bar for polymers to understand its behavior.
Sir. Thank you, sir.
Well, thank you, sir. Thank you for your answers. Is there any other questions from the participant side? Shall we close the questionnaire session from participants? Is there anyone? You may ask question. I think that's it, sir. Okay, thank you, sir. I would like to convey my sincere thanks and our gratitude on behalf of the Department of Aeronautical Engineering for accepting our request and invitation for this 5 days FDP program. And this session was really informative, and hope all the participants around the world, those who are attending this session, has gained a lot of knowledge. Thank you very much, sir. Once again, thank you very much for accepting our request and being here. So it was a pleasure to have you here.
Thank you.
Sir. Thank you so much.
Thank you, Mr. Tamilvendan. Thanks for inviting me. I thank the organizer also. Thank you very much.
Thank you, sir. Thank you. Thank you, participants. That's all from today's morning session. And don't miss the afternoon session. So today afternoon, we have another guest resource person, Dr. Dinesh Manoharan from the UCall Aerospace, UCall UAV Systems. So he'll be giving his lecture by 2:30 p.m. So do not miss the session. So I expect all of you to be in the session. And the feedback links are already shared in the group. You may check the chat box. The feedback link is available there. It will be closed automatically in 1 hour. So kindly post your feedbacks there. So we'll again meet by 2:30 p.m. with our guest, Dr. Dr. Dinesh Manager from you. So thank you for being here. Hope you have enjoyed the session. See you soon. Thank you. you.